The universe is hiding something about its own childhood. Astronomers have found supermassive black holes, fully grown, in places where the universe was still an infant. They were colossal giants, and they had no time to exist. It's an impossible finding. It started a race to rewrite the story of cosmic evolution. How did these monsters appear so early? What does their premature existence tell us about the chaotic dawn of time itself? The evidence starts with brilliant quasars. They were the first clue, the first betrayal of the secret. Now space telescopes are hunting for answers. This is a detective story, written in the fabric of space-time. Every clue forces a reconsideration of everything. The cosmos is defying its own rules. That newborn baby, impossibly huge, that's not a metaphor. That's the actual scale of the problem. The universe was only a few 100 million years old, and these giants were already there. You have to picture that time. The first stars are just starting to light up. Cutting through a fog of hydrogen, galaxies are these fragile, wispy things, just beginning to pull themselves together. It's the cosmic dawn. Everything is delicate. Just beginning, and yet, inside these infant structures we find black holes with masses billions of times our Sun, already fully formed, and by every standard model of how things grow, this isn't just unlikely. It's impossible. A supermassive black hole should be the final product, the end result of a galaxy's entire life, billions of years of feeding, of mergers. It's the grand finale, not the opening act. Finding one this early is like finding the skeleton of a giant in a newborn's cradle. The timelines don't match. The growth charts are all wrong, and that contradiction forces a question. Did the story of the universe's largest structures begin with a slow climb? Or did it start with a shortcut, a colossal, inexplicable shortcut? So the race to explain these black holes, that race is really about finding that missing chapter. The one that rewrites the whole biography of the cosmos. That ancient light is a messenger. It's carrying a story from the very edge of time. Astronomers first saw these brilliant beacons, quasars, and they knew it was something special. But they didn't understand the full weight of the message. A quasar isn't a single object, it's a catastrophic event. You picture the heart of a young galaxy. A supermassive black hole sits there, and around it this vast, swirling disk of gas. As the gas spirals inward, it doesn't just vanish, it heats up. To millions of degrees, it screams with energy, blasting out radiation so intense it can outshine every star in its galaxy combined. That ferocious beacon is the quasar. It's the universe's most powerful lighthouse, and for us, it's a perfect tool, because that brilliant light travels across billions of light years, and it carries a precise fingerprint. Astronomers can split the light into a spectrum, a rainbow of information, and within it they can read the subtle shifts and lines. Those reveal two crucial facts. The first is the black hole's mass. By measuring how fast the gas whirls around the center, they can weigh the invisible monster. The second is its appetite. The brightness tells them how much material is falling in, how voraciously it's feeding. For decades, this was how we studied black holes in the mature universe. Then the telescopes looked deeper. They found quasars whose light had been traveling for over 13 billion years. That meant we were seeing them when the cosmos was an infant. Only a few 100 million years old, and the message in that light was shocking. The fingerprints revealed black holes, not modest seedling sizes, but behemoths. Already weighing over 1 billion solar masses, this was the first concrete clue. The universe's announcement that its rulebook was missing pages. These quasars weren't just distant. They were impossibly mature. That brilliant scream across the ages forced a single question onto the table. How do you build a billion-sun monster in the time it takes the universe to blink? The brilliant quasars were the first sign. They were screaming out there in the dark, but they were just a clue. To solve something like this, you need more than a clue. You need the whole scene, and that takes different tools, different detectives. Hubble was the first. It found those beacons, pinpointed them way out in the ancient void. But Hubble saw the end of it, the finished product shining bright. To see the beginning, you had to look earlier. You had to see the nursery, the dusty, murky clouds where these things are born. That's where Webb comes in. Webb has infrared eyes. It doesn't just see light, it sees heat, so it can look through the dust that shrouds the earliest galaxies. It finds black holes that are so young, so faint, they were invisible before. It's like switching from a flashlight to a thermal camera in a dark room. And suddenly you see the warm shapes, the infant monsters hiding there. But even that's not the whole picture. To understand how they grow, you have to see what they eat. The gas, the dust swirling around them, the raw material. For that, you look from the ground with something like ALMA, the Atacama Array, a collection of radio dishes up in the Chilean desert. ALMA doesn't take pictures of stars, it listens, it tunes into the radio whispers, the faint signals from cold gas and dust. It maps the reservoirs, the chaotic swirl that feeds the hunger of a young black hole. So it's a coordinated thing. Hubble finds the suspect, Webb looks at its hidden childhood, and ALMA analyzes the scene, the evidence. Every new observation from these tools, it adds a data point. It shrinks the space where a theory can live. An idea can sound elegant on paper, but if the data from Webb shows a black hole existed 200 million years earlier than the idea allows, then that idea is done. The theory is finished. The floodgates are open now. We're not looking at a single, confusing photograph anymore. We're watching a film reel of the universe's infancy. Frame by frame, and with each new image, each slice of data, we get closer. Maybe not to a simple answer, but to the right questions, to the deeper mystery behind that first impossible fact. The standard model says things grow slowly. It starts with a seed. After the Big Bang, the first stars light up. They're huge, hundreds of times the mass of our sun. They burn fast and die young. When one runs out of fuel, its core collapses, not into a white dwarf, into a black hole. That's the seed, maybe 10, 100 solar masses. So the story goes, this seed sits in a young galaxy. It pulls in gas, it merges with others. Over billions of years, it feeds, it grows. Like a tree from an acorn, with enough time, it becomes a giant. It's an elegant process, logical. It fits the mature universe we see. But when we look back to the beginning, the timeline breaks. The math doesn't work. There's a basic calculation. A black hole can only eat so fast. There's a limit, the Eddington limit. If it eats too fast, the radiation pushes the gas away. It shuts off the food. So even if a seed ate at the maximum rate, non-stop, for its whole life, it still couldn't reach 1 billion solar masses in just a few 100 million years. The numbers don't add up. It's a time crunch. The seed is there, the giant is there, but the billions of years of growth are missing. This isn't a small gap. It's a chasm. The gradual story of cosmic gardening can't explain these ancient giants. The seed theory isn't wrong, but it's incomplete. It's under pressure. Bending from impossible evidence, and when a comfortable model breaks, that's when science gets interesting. That pressure forces a leap. It makes us ask a question. What if the seeds were never small? The seed couldn't grow fast enough, so maybe the seed was never small. That's the first radical theory, the direct collapse model. It proposes a shortcut, a profound one. It rewrites the first chapter. It asks us to imagine a universe before stars, dark and quiet, filled with vast clouds. Pristine hydrogen gas. In the standard story, these clouds fragment. They break into smaller clumps. Each clump ignites as a star. But what if that didn't happen? What if a cloud held itself together under just the right conditions, without stars to stir it up, without heavy elements to cool it down? This immense cloud could simply collapse. Not into a cluster of stars, but into a single point, a catastrophic point, a direct headlong fall. The result wouldn't be a stellar mass black hole. It would be a behemoth from birth, a seed already tens of thousands of times the sun's mass, even hundreds of thousands. It's the difference between planting an acorn and planting a full-grown oak tree. With that kind of head start, the timeline makes sense. This massive seed has more gravity. It can pull in gas more efficiently from the start. It can race toward supermassive status. In the brief window of the universe's infancy, the elegance is its simplicity. It doesn't require new physics. It just requires a different starting condition. A cosmic accident on a grand scale, a cloud that never fragmented, that fell into itself whole. But like any good theory, it has questions. How common were these special clouds? These pristine clouds, what specific conditions prevented star formation? The model paints a picture of a rare, violent birth, a singularity born not from a dying star, but from the raw material of creation itself. It's a compelling contender, a way to build a giant fast, but is it the only way? The direct collapse model is a shortcut. But it still needs a specific event, a unique cloud early on. There's another path, a more radical one. It removes the need for any formation event at all. What if these black holes weren't born from stars or from clouds? What if they came from the universe itself, from its very first breath? That's the idea behind primordial black holes. The name tells you, primordial, from the beginning. The thought is, in the first chaotic moments after the Big Bang, the universe wasn't perfectly smooth. It was a seething, turbulent sea of energy, and in that sea there would have been knots, ultra-dense fluctuations, places where the density spiked so high that gravity just won. Right then, not from a star collapsing billions of years later, but from a random, violent pinch in the fabric of the newborn cosmos, those knots could have collapsed directly into black holes. And they could have been any size, from something as small as a mountain to something as vast as many stars. That's the crucial part. If they formed in that first second, they were there from the start. They had the maximum possible time to grow, over 13 billion years. A black hole seed that existed when the universe was less than a second old has an unimaginable head start. It could begin pulling in matter almost immediately. It could be the ready-made kernel, the gravitational anchor, where the very first wisps of gas gathered to form the first galaxies. So think of it this way. In the standard story, a galaxy forms first, and a black hole grows inside it. In this story, the black hole comes first, and the galaxy grows around it. The galaxy is the consequence, not the cause. This idea is elegant because it connects two separate worlds, the physics of the unimaginably small quantum fluctuations, directly to the birth of the largest structures we see. It offers a bridge between the rules for subatomic particles and the rules for the cosmos. It suggests the seeds of cosmic giants were sown in the furnace of creation itself. It is, of course, highly speculative. We've never confirmed a single primordial black hole, but as an explanation for our impossible infant giants, it's thrilling. It places the origin of the mystery not in the nursery of stars, but in the first instant of everything. If true, it means the blueprint for the cosmic web, for galaxies and their dark hearts, was written into the universe in its first fleeting moment. A signature of chaos frozen in gravity, waiting billions of years to be seen. But the seed could have been ordinary, and the growth was what was extraordinary. That's a third idea. It changes the rules of the meal itself. There's the Eddington limit. It's a speed limit. A black hole can only eat so fast before the radiation from its own meal pushes the gas away. It shuts off the food supply. It's a natural break, a balance, but what if that break failed? In the chaos of the early universe, What if a black hole could binge? That's the theory of Super-Eddington accretion, super meaning above, beyond. It suggests the rules were different in those first galaxies, dense, gas-packed nurseries. The buffet was too overwhelming, too messy. It's like trying to drink from a fire hose. The water comes in faster than you can swallow. It gets everywhere. That's the picture, gas and dust flooding inward in thick, turbulent streams. The radiation couldn't push it all back out. The black hole wouldn't be a polite diner. It would be a ravenous vacuum, gulping down material in a frantic, inefficient feast, but incredibly rapid. It wouldn't be a steady diet. It would be a series of colossal cosmic gorges. A stellar mass seed from the death of a first star could balloon in size, staggering rate through these episodes. It solves the time problem not with a bigger seed, but with a faster metabolism. A shortcut through gluttony, this idea has a visceral appeal. It fits the early universe as a wild, untamed place, a realm of excess where the normal laws of physics were stretched to their limits. It turns the black hole from an elegant engine into a messy, chaotic force, and it might not be just theory. Some quasars from that era show signs. Their light suggests feeding in fits and starts, in tremendous bursts, as if we're catching them in the middle of one of these historic binges. So we have three paths now: a massive seed from direct collapse, an ancient seed from the Big Bang itself, or a normal seed that ate its way to glory by breaking all the dietary rules. Each path leads to the same impossible infant giant in the telescope. But they paint wildly different pictures of the universe's first chapters, one of orderly collapse, one of quantum birth, and one of chaotic, glorious gluttony. The race isn't just to pick one, it's to see which picture fits, or what combination of them fits the evidence that is still pouring in. There's a fourth player in this story. One that's been there from the start, an invisible architect, dark matter. We know it makes up most of the matter in the universe, 85%. It doesn't shine, it doesn't absorb light. We only know it's there because of gravity. It forms these immense, ghostly halos, cocoons that cradle every galaxy we see. In the standard story, dark matter is the framework, the hidden skeleton everything else is built on. It pulls gas in slowly over eons, but what if in those frantic early days dark matter did more than just pull? What if it was an active catalyst, a cause for catastrophe? Some theories say in the infant cosmos, dark matter wasn't smooth. It could have formed ultra-dense knots, clumps of pure, concentrated gravity. Think of them as deep, invisible wells in space. When the first clouds of hydrogen drifted through, they would have fallen into these wells. Not gently, with ferocious speed. That intense, localized gravity would have compressed the gas violently, and that could have done one of two things. It could have triggered the formation of those impossibly massive first stars, the ones that later collapse into large seeds, or even more directly, it could have forced a cloud to collapse so fast, so completely, that it skipped star formation entirely, going straight to a direct collapse black hole. So in this view, dark matter isn't just a passive scaffold. It's the hidden hand that sets the table. It provides the extra gravitational oomph, the jumpstart, needed to build a giant on a deadline. This idea ties the two great mysteries together: the mystery of the unseen dark matter that shapes everything, and the mystery of the supermassive black holes that appeared too soon. They're not separate puzzles, they're part of the same design. The luminous behemoths we see blazing in the early universe, they might be the signatures. The brilliant signatures of dark matter's first and most dramatic acts of creation. Those theories need a stage, a place to happen, and the early universe was that stage. It was the perfect place for monsters, but not a calm place, a violent one, a chaotic one, and a rich one. You have to understand the context. You can't understand these infant giants without the world they came from. It was denser, it was hotter, space was more crowded. You had these vast oceans of gas, pure gas, swirling in the dark, just hydrogen and helium, nothing else. No carbon, no oxygen, no iron. That purity matters. In our universe now, gas clouds have heavy elements, metals, and those metals act like a radiator. They let the gas cool gas fragments. It breaks into lots of small clumps, and each clump makes a small star. But if you take those metals away, if you have just hydrogen and helium, that cloud can't cool as easily. It stays hot, it stays puffy, it resists breaking apart, so when gravity pulls, the whole cloud can collapse. All at once, as one single gigantic thing. It's the difference between a fog bank turning to mist and a fog bank collapsing into one massive droplet. That's the environment. That's what makes the direct collapse model possible. A place where star formation gets suppressed, not from an absence of material, from a lack of the ingredients for fragmentation, but that's just the raw material. The dynamics were different too. It was a frontier. Everything was moving. Crashing together, you had these small proto-galaxies, wispy collections of gas and the first stars, and they were constantly merging. It was a cosmic demolition derby. And with every merger, chaos, gas clouds slamming together, losing their orderly orbits, vast streams of fresh fuel funneled violently toward the centers. Any black hole seed sitting there would find itself at the center of a sudden feast, a catastrophic feast. This wasn't steady growth, this was growth by avalanche. By sudden, overwhelming plenty. The early universe wasn't playing by the slow rules, the careful rules of the modern cosmos. It was writing its own rulebook. A rulebook of abundance, of violence, of pure, unregulated potential. It set the stage not for gradual evolution, but for explosive leaps, accelerated leaps. So when we look at those quasars, those brilliant, impossible quasars, we're not just looking at a black hole, we're looking at the product of an entire era. A specific, fleeting moment, a moment in cosmic history when the conditions were just right, or just chaotic enough to build a billion-sun giant in the blink of a universal eye. That environment is gone now, polluted by generations of stars, calmed by expansion. We are left with the fossils, these ancient giants blazing in the dark. They are relics of a wilder, more fertile time. The theories are bold, they live in the realm of possibility, but to test them you need an experiment. And you can't experiment on the universe, you can't rewind time, plant a different seed and press play. So scientists built the next best thing, a time machine made of silicon and code. They're building entire universes inside supercomputers. These aren't simple animations. They're staggeringly complex digital laboratories. The rules are written in. The laws of gravity, the behavior of gas under pressure, the subtle push of radiation, the recipe for star formation. Every known piece of physics gets encoded into billions of lines of instructions. Then they set the initial conditions. They create a virtual cosmos a fraction of a second after the Big Bang, and they let it run. They watch it evolve over billions of virtual years, compressed into weeks of supercomputer time. In this digital cosmos, they can plant different seeds. They can start with a pristine cloud of hydrogen and see if it collapses directly into a massive black hole. They can sprinkle in primordial black holes from the first instant and watch galaxies form around them. They can take a stellar seed and flood its virtual galaxy with gas, turning off the Eddington limit to see if a binge can create a giant. Each simulation is a separate universe with its own history, and the outcome gets compared meticulously to the real data. Does this virtual universe, after 13.8 billion simulated years, produce quasars that look exactly like the ones Webb and Hubble see? Does the distribution of galaxies match? The simulations are the proving ground. A theory might sound elegant, but if it can't produce the universe we actually observe inside the machine, it falters. These digital experiments have become the crucial battleground. They let researchers witness cosmic evolution in fast-forward, to rewind and replay, to isolate single variables in a way nature never allows. When a simulation succeeds, when its virtual quasars blaze at the right time with the right brilliance, it sends a jolt of excitement through the community. It means a path is plausible. When it fails, it forces a painful but essential return to the drawing board. The supercomputer becomes a judge, weighing the evidence of imagination against the unyielding laws of physics. It's here, in these rivers of electrons, that the fate of our cosmic origin stories is being decided. The supercomputers run the simulations, but the verdict comes from the sky. From the data, and for the last 2 years, one instrument has been rewriting the evidence. The James Webb Space Telescope is the great referee. Its launch in 2021 was a revolution waiting to happen. A time machine with a gold mirror built to see the universe's first light. Its primary mission was to find the earliest galaxies, the first stars, but it's become, almost by necessity, the premier hunter for the universe's first monsters. Because of its vision, Webb doesn't see the universe like our eyes do. It sees in infrared. It feels the heat. When light from the most distant objects travels for over 13 billion years, the expansion of the universe stretches it. Shifts it from visible light into the infrared. To other telescopes, that light is invisible. To Webb, it's a clear signal, and infrared light pierces cosmic dust. The thick shrouds that hide the nurseries of young galaxies and their black holes, Webb pulls back that veil. It reveals the faint, warm glow of accretion disks. Around black holes so young they were only theoretical, every new deep field image from Webb is a treasure map. Astronomers scour it pixel by pixel, not just for galaxies, but for the specific signature of a supermassive black hole in its infancy, a pinpoint of intense infrared light at a galaxy's heart. A compact, furious energy source that can't be explained by stars alone. Each discovery is a data point, and Webb is providing a census. Before Webb, we had a handful of these impossible infant giants. They were the brilliant, screaming quasars. The obvious freaks, but were they freaks, or were they the tip of an iceberg? Webb is answering that. It's finding black holes in smaller, fainter, more ordinary galaxies from the same era. It's building a population, and that population data is what will kill theories or give them life. If Webb finds that every single early galaxy, no matter how small, harbors a massive black hole that points to a primordial origin, a seed baked into the universe's fabric from the start, if it finds them only in the biggest, densest, most chaotic galaxies, that supports the direct collapse model. A rare, special event, and if it finds a mix with some growing impossibly fast, that points to chaotic Super-Eddington feasting as the key. Webb isn't just taking snapshots. It's taking attendance. It is asking the cosmos a direct question. How common was this? And the universe, for the first time, is beginning to whisper back an answer. Every new dataset from this golden-eyed telescope shrinks the room for speculation. It brings the phantom of the early universe into sharper focus, a more demanding focus. The cosmos has a soundtrack. It's been playing for billions of years in silence, a vibration we couldn't perceive, but then that changed. We learned to listen. Not to light, but to the fabric of reality itself. Gravitational waves, they're the deep notes of this symphony, ripples in spacetime sent out by the most violent events. The collision of black holes, when two of these invisible giants spiral together and merge, they shake the cosmos. They send out a wave, a distortion that travels at light speed, stretching and squeezing everything it passes. For over a century, this was just a prediction from Einstein, a beautiful idea. Then, in 2015, we heard it. LIGO caught the first signal. A tiny chirp, a fraction of a second. It was the sound of two stellar mass black holes over 1 billion light-years away crashing together. That was proof. The universe was speaking in gravity, and we had just learned its language. This new sense, this ability to hear, it changes the race to explain our infant giants. Because telescopes like Webb show us the brilliant ones, the black holes shining with light, the ones that are feeding, but the quiet ones, the ones in the dark between meals just orbiting each other. The ones about to merge, light can't show us that, but gravity can. Every merger has a signature, a specific chirp in the data. The pitch and tempo of that chirp tells a story. It reveals the masses of the black holes, their spins, even the distance. By collecting enough of these signals, we can start to build a census, a history book written not in light but in space-time tremors. We can ask across cosmic time, how often did black holes merge, and how big were they when they did? This is the crucial line of evidence. If the infant giants grew through rapid, chaotic mergers in the early universe, that history should be etched into the gravitational wave background. A faint, persistent hum from countless collisions across time. Our current detectors, LIGO and Virgo, they hear the high notes, the mergers of stellar mass black holes and neutron stars. To hear the bass line, the mergers of the supermassive giants, we have to go to space. That's the promise of a mission like LISA. Imagine 3 spacecraft floating millions of miles apart, connected by lasers. They'd form a detector so vast, so sensitive, it could hear the mergers of billion solar mass black holes from the dawn of time. It would listen for the slow, deep chirps of these monsters spiraling together over millennia. The data would be a direct recording of their assembly, a soundtrack of growth. So we're building a complete picture. Webb and Hubble give us the visuals, the portraits of these giants in their youth. Gravitational wave astronomy gives us the audio, the record of their violent dances. Together, they form a story no single sense could tell. We're no longer just watching the cosmic dawn. We're learning to hear its birth cries. The rhythm of those first collisions may soon be more than theory. It may be a signal waiting in the quiet between the stars. A black hole's hunger is its own biggest enemy. That's the feedback paradox. You have this cosmic tug of war right at the center of a young galaxy. Gas spirals in. It heats up to incredible temperatures. It blasts radiation back out, and that radiation pushes against the gas still coming in. And then you also get these jets. Huge jets of magnetized particles erupting from the poles. They drill out into the surrounding gas clouds for thousands of light years. That's not just a side effect. It's a regulatory system. The black hole's own feast creates a violent wind, a wind that can clear the table. It heats the galactic gas so it can't cool down and fall in. It can even blow that gas clean out of the galaxy. So the process of rapid growth, it contains the seeds of its own limitation. It's self-governing. For a black hole to become supermassive and to do it quickly, it has to solve this. It has to either eat with such staggering force that it overwhelms its own feedback, like a fire so hot it consumes its own smoke, or it needs an environment of staggering abundance. So much gas keeps coming, it's a relentless flood that no wind can push away. The early universe gave you that second condition. It was a place of profound density. Gas reservoirs were vast, constantly replenished by mergers and inflows. A young black hole could be a furious engine and a messy eater, with so much fuel in the room it couldn't blow it all away. That balance changes how you see these objects. They're not passive pits in space, they're active. They shape their own destiny and the destiny of their galaxies. Their growth isn't a solitary act, it's a conversation. A violent, energetic dialogue between gravity and radiation, between collapse and expulsion. To build a giant, you don't just need a big seed or a fast meal. You need an environment that lets the feast continue, even while the guest of honor is shouting at the top of its lungs. J1342 plus 0928. It's a quasar, a cosmic landmark. Astronomers found it in 2017, and it wasn't just a record, it was a challenge. We see it from when the universe was 690 million years old, just a toddler, and at its center, a black hole, already 800 million times the mass of our Sun. That's the whole paradox right there, a measured giant, a fully formed colossus looking back at us from the dawn. Its light has traveled over 13 billion years. Scientists took that light, split it into a spectrum, and read its environment. The galaxy around this monster is creating stars furiously, far faster than our Milky Way. But the gas falling into the black hole itself is pristine, metal poor. It lacks heavy elements, so the black hole grew up in a place that was both wildly productive and primitive. It was feeding on the virgin gas of the early universe, even while the first stars were polluting the galaxy around it. This quasar is the ultimate test case. Any theory about infant giants has to account for this object. Its mass, its age, its surroundings, its Exhibit A, a direct confrontation between what we think is possible and what the universe shows us. This one point of light forces every idea to prove itself. Did it grow from a seed, collapse from a cloud, or binge on gas in a chaotic young galaxy? The answer has to fit the data from this one impossible benchmark. It stands as a silent judge. Its brilliance is a question mark over every simulation. To solve the mystery of the early giants, you have to understand this one. A stellar seed, even a large one, is just part of the story. You have to look at the first light. Before galaxies, before quasars, the first suns, astronomers call them population 3 stars. They're the pioneers, made from the original hydrogen and helium. They're the missing link. Theory says they were titans, hundreds of times the mass of our Sun, behemoths of pure hydrogen burning a fierce blue-white. Their lives weren't billions of years but millions, a brief flash, and their deaths were cataclysmic. When a star like that runs out of fuel, its core collapses. Not into a white dwarf but into a black hole, a stellar mass black hole but starting from a much larger foundation, a seed of maybe 100 solar masses instead of 10. That's a significant head start. It cuts the growth time down, but there's another factor. These first stars probably didn't form alone. They were born in dense clusters, siblings in a violent nursery. When they died, their black hole remnants would be left orbiting each other in that tight space. Gravity pulls them together, they merge. 200 solar masses becomes 400. 400 becomes 800. In the crowded core of a young protogalaxy, this chain reaction of mergers could build a substantial seed, and fast. It's a different kind of assembly, not just feeding on gas but cannibalizing its own kind. This path turns a cluster of dead first stars into a single, growing anchor. The hunt for population 3 stars is a parallel race. No telescope has ever definitively seen one. Their light is so ancient, so stretched, it likely falls into an infrared signature that only an instrument like Webb might tease out. Finding even the ghost of one would be monumental. It would provide the crucial context. Were they truly the monsters theory predicts? Did they leave behind the graveyards of black holes that the models need? They represent the bridge, the luminous bridge between the Big Bang's afterglow and the dark hearts we find blazing too soon. To understand the seed, you have to find the star that made it. And in doing that, you might trace the lineage of these cosmic giants back to the very first dawn. The puzzle asks for more than one answer. You have the big theories competing. But there are other possibilities, ideas that work differently. One of them looks at a young galactic core when it's chaotic. You imagine it not as one single pit, but as a crowded arena. Several massive black hole seeds from that first generation of stars, all orbiting in the same dense, violent space. They wouldn't stay separate. Gravity pulls them into a complex dance. A binary system, maybe even a triple, and in that dance there's a chance for a shortcut, a gravitational slingshot. As these objects whip around each other, there's an intricate exchange of energy. One black hole could be flung inward toward the very center of the galaxy at tremendous speed, carrying immense kinetic energy. The others might be ejected, thrown out into the dark intergalactic void. Cosmic orphans, the victor, the one that wins the slingshot lottery, is now alone at the center. It has a clear, unchallenged claim to all the gas swirling there. With no competition, its growth accelerates dramatically. It's a path to dominance not just through feeding, but through a violent game of gravitational king of the hill. Another speculative path looks to the densest star clusters. In these swarms, thousands of stars are packed into a tiny volume. When the most massive ones die and leave behind black hole seeds, those seeds sink to the cluster's heart. In that tight knot of darkness, mergers could happen at a staggering rate, a runaway chain reaction. Two become one, that new object quickly finds another partner, and the process repeats. In a short cosmic span, you could build a surprisingly massive object through pure cannibalism. This intermediate mass black hole could then sink to the center of the young host galaxy, becoming the ready-made core for a future supermassive giant. These ideas are less mainstream. They involve specific, almost finicky conditions, but that's their value. They represent the creative, out-of-the-box thinking this impossible discovery has ignited. They remind us the solution may not come from simply scaling up a known process. It might arrive from an unexpected corner of astrophysical dynamics. A subtle gravitational interaction we haven't fully considered. A chaotic environment we haven't perfectly simulated. The very existence of these alternative paths is a testament to the depth of the mystery. It tells us the universe, in its infancy, had more than one way to build a monster. Our job is to listen to the evidence and find out which way it chose. This race isn't just a technical puzzle, it's deeper than that. It questions a story we've held for a long time. We have this grand narrative for the cosmos. It begins with a hot, dense, nearly uniform state. Then gravity works over immense time. Tiny ripples grow, gas condenses, the first stars flicker on. They gather into galaxies, and over billions of years within those galaxies, black holes emerge, they grow. It's a story of gradual emergence, complexity from simplicity. Order from chaos, a patient unfolding, but these infant supermassive black holes stand against that. They aren't a product of that long unfolding, they challenge the timeline. If these dark giants were fully formed when the universe was in its cradle, it suggests a different beginning, one where the most extreme objects weren't the end result. They were the starting point, the anchors, the gravitational seeds, everything else coalesced around them. This inverts the relationship. For decades, we saw a supermassive black hole as the crown jewel of a mature galaxy. The final, dark ornament at the heart of a vast city of stars. But what if we had it backward? What if the black hole came first? A massive knot of gravity in the primordial darkness, pulling the first gas toward it. That gas forms stars. Those stars build the galaxy. In this version, the galaxy is the consequence, the luminous byproduct of a dark heart's hunger. The philosophical stakes are quiet but immense. It reshapes our place. If black holes are foundational, not derivative, then the cosmos we inhabit, the spiral arms, the star clusters, the planets, all of it grew in the shadow of these ancient monsters. Our existence might be an echo of a gravitational seed planted in the first instance. It challenges our intuition about growth. We see a universe that built itself from the small to the large. But the evidence whispers the blueprint might have been written in reverse, that the largest structures were there in potential from the very start. Solving this won't just fill a gap in a textbook. It will rewrite a chapter in the story of what we are, where we came from, how the fabric of reality chose to weave itself into being. This mystery is a bridge. It crosses the biggest gap in science. On one side, there's particle physics, the world of the incredibly small, quantum ripples in an energy field. On the other side, there's cosmology, the study of galaxies, clusters, the whole cosmic structure. For a long time, these two fields worked separately. They spoke different languages, looked at different scales, but the infant black hole problem has changed that. It's become a meeting place, a single, stubborn fact that forces both sides to talk. Take the primordial black hole idea. It says these giants came from knots in the fabric of the very early universe. To test that, you have to understand those first moments. You need the physics of inflation, that explosive expansion in the first tiny fraction of a second. Particle physicists model this. They work out the density of that early energy. They predict how it might have rippled, how it folded. Their equations describe the possible seeds. Then they hand that data over to the cosmologists running the supercomputer simulations, who put those seeds into a model universe and watch to see if galaxies form right around them, if the simulated sky ends up matching what Webb sees. This is a deep collaboration. It means a theorist working on quantum gravity and a scientist mapping gas clouds in a far-off galaxy are now reading the same papers. They're going to the same conferences because the clue to the galaxy mystery might be hidden in the math of the first microsecond, and the evidence for that microsecond might be written in the light from a quasar 13 billion years old. It's a convergence. One observation, these impossible giants, has become a focal point, a place where different strands of knowledge have to come together. The specialist in the very small and the expert in the very large now have to learn a common language. They have to translate between quantum fields and galactic mergers. This puzzle won't be solved alone. It insists that reality is one connected thing, that the laws for a subatomic particle are tied to the fate of a supermassive black hole. And by forcing that dialogue, it's weaving a fuller picture, a more complete story of where everything comes from. The search for these ancient monsters is doing more than rewriting cosmic history. It's changing how we look for understanding, the search for answers in the cosmos. It demands tools of staggering ambition, and this intellectual race, it's powered by a real engine. Steel, silicon, human ingenuity, the James Webb Space Telescope, the future LIS Observatory, the colossal ground-based telescopes being built now. These aren't just instruments, they're cathedrals of curiosity. Each one is a monumental investment, billions of dollars, decades of work, thousands of scientists and engineers and technicians across the globe. They're feats of international diplomacy. They push the limits of material science, precision engineering, software design, to build a mirror over 6 meters across. Launch it 1,000,000 miles from Earth, have it unfold perfectly in the frigid void. That ambition alone, it reshapes what we think is possible. It creates a legacy of technology. Technology that filters down into our daily lives. Then there's the data, the torrent from these observatories, every pixel from Webb's deep fields, every subtle chirp in a gravitational wave detector. Processing that drives innovation in computing. It demands new algorithms, artificial intelligence to sift the cosmic signal from the noise, to find the faintest, most distant quasars in a sea of data. This pursuit, it fuels a high-tech ecosystem. It creates specialized jobs, optics fabricators, data visualization experts. It inspires students to look at a problem not as a barrier, but as a challenge to be engineered away. So the quest to understand an ancient black hole, a pinprick of light from 13 billion years ago, that becomes an engine for progress, right here, right now. It reminds us that asking the biggest questions, it doesn't just expand the universe out there, it builds a better world down here. This is more than just data. It feels like a story we're in. There's a reason a headline about a new quasar, something Webb found, grabs people outside of astronomy. It touches something basic, a human love for a real mystery, and this is the coldest case, written in light and gravity. It's a detective story happening right now. The whole cosmos is the scene. Every press release is a clue. Every new paper is a plot twist. We're not just watching, we're the audience, watching the biggest puzzle anyone's ever seen slowly come into view. The stakes aren't personal, but they're deep. They're the origin story of everything. That narrative has its own gravity. It pulls you in. The visuals feed that. Artist concepts based on real data show these infant galaxies, a swirling storm of gas and dust, lit by the first furious stars, and at the center, a dark pit. A pit in space-time, ringed by a disk of fire. It's pure awe. It takes abstract ideas, distances so large they numb you, and makes them feel dynamic, alive. It shows a universe that isn't static, isn't silent, but a place of violent creation and deep questions, questions without answers. This public captivation isn't a side effect. It's part of the engine. That widespread wonder becomes support. It helps justify the investment in tools like Webb, in the next telescopes. It makes a child look up at the night sky and not just see dots, but see frontiers, to ask a question that could become their life's work. When we follow this race, from an announcement about an impossible quasar to the latest simulation, we're doing more than reading science news. We're participating, we're witnessing a grand human endeavor, the endeavor to look into the deepest dark, to find a point of impossible light and to ask it. Gently, relentlessly, to tell us where we came from. In that act of asking, we connect the human experience to the cosmos. Directly, we make the universe a shared home. Full of stories still waiting to be read, but the real science, it doesn't happen in the quiet. It's in the noise, the argument, the race to explain these giants. It's not calm. It's a heated debate, a global one. In university halls, in journals, you have the direct collapse model. Proponents run their simulations, show how a pristine cloud could just fall into itself. And then you have the other side. They push back. They champion Super-Eddington accretion. A normal seed, they argue, could binge its way to a supermassive black hole if the conditions were chaotic enough. Every new paper is a salvo, every conference talk a challenge, and then there are deeper doubts, fundamental ones. Skeptics ask a crucial question: are we even reading the evidence right? When we measure a quasar's mass billions of light years away, we rely on models of how gas moves in that ferocious disk. But what if the models are wrong? Subtly wrong. Could we be overestimating the masses by a factor of 2 or even 10? That alone would shrink the problem, make the growth timelines more plausible. Others ask about cosmic illusions. Could gravitational lensing be at play? A foreground galaxy warping the light, magnifying these distant quasars, making them appear brighter and therefore more massive than they really are. These aren't fringe ideas, they're essential checks. The process demands them. And then there are the radical proposals. A few researchers suggest what we're seeing might not be a black hole at all. Not yet. It could be a supermassive star, a hypothetical object, a quasi-star. Picture a star, immense, hundreds of thousands of times the sun's mass. Its core collapses under its own weight while the outer layers are still puffed up. A black hole forms inside it, like a pit in a cosmic peach, and it feeds on the star's own substance from within. This bizarre object could shine like a quasar, but its heart would be different, a black hole in the making, not a finished product. This idea stretches stellar physics to its limit. But it exists because the data forces creativity. These debates, they're not a weakness, they're the engine. Every challenge, every skeptical question, it's a stress test. It forces each theory to prove itself, to account for every piece of contradictory data. It stops the community from falling in love with a beautiful idea that doesn't fit. The controversy is the filter. Through this noisy, rigorous process, the fragile ideas fall away. The robust ones, the ones that withstand the barrage and still match the observations, they grow stronger. The destination isn't a simple, elegant answer. It's a more complex picture, a more nuanced one, a more truthful picture of a universe that refuses to be simple. That's how you move from mystery through conflict closer to understanding. The debate sharpens the questions, and the questions guide the hunt, so a new target has emerged from the theoretical work. A specific prediction. Astronomers call them overmassive black holes. The name is a clue. It means the black hole isn't just large, it's disproportionately huge compared to its galaxy. Think of a tiny village, and in the middle, a single towering castle that dominates everything. That castle wasn't built by the village, it was there first. Or built by different rules. In cosmic terms, it's a David and Goliath story, where Goliath lives in David's backyard. This is a key prediction of theories like direct collapse. If a black hole forms from one massive event early on, it gets a colossal head start. It can grow rapidly while its host galaxy is still just a wisp of gas. A few fledgling stars. For a long time, the galaxy struggles to catch up. The result is an imbalanced system, a behemoth heart in an infant body. The standard model is different. It suggests co-evolution. The black hole and its galaxy grow together in lockstep over billions of years. Their masses should be proportional. An overmassive black hole shatters that. It's a potential smoking gun for a different origin story. So the investigation enters a new phase, more precise. The James Webb Space Telescope isn't just looking for any early black holes now. It's conducting a census with a specific profile. Astronomers are hunting for the faintest, smallest galaxies from the cosmic dawn and peering into their hearts. They're asking a more nuanced question. Not just do supermassive black holes exist early, but what is their precise relationship with their galactic homes? Is the giant always with a giant galaxy, or do we find these monsters lurking in cosmic backwaters? Every candidate system Webb identifies gets scrutinized. Scientists measure the mass of the stars in the faint host galaxy. Then they measure the mass of the central black hole, inferred from the energy blazing from its core. They're looking for the outliers, the systems where the ratio is wildly off, where the black hole's mass is a significant fraction of the entire galaxy's stellar mass. Even a majority, finding even a handful of these would be revolutionary. It would tell us that in the universe's first chapters, black holes could be the prime movers, the anchors around which everything else reluctantly gathered. This search refines the mystery. It moves us from a simple shock of existence to a deeper study of relationship. It's detective work that compares alibis. If the black hole and galaxy grew up together slowly, their stories will match. If the black hole has a wild, accelerated past, its story will dwarf the quiet tale of the stars around it. Each new image from Webb is a piece of testimony, each spectrum from a faint, ancient smudge of light, and we are the jury, listening carefully, trying to discern which story the universe is telling us about its own tumultuous childhood. The late 20th century had this quiet prediction. Theorists, using the known laws of physics, they sketched out the universe's first chapters, and the first black holes, they would be modest. Stellar remnants, they would need immense time to grow into the giants we see. It was a logical forecast, a gradual, orderly cosmos. Then the Sloan Digital Sky Survey began. A robotic telescope mapping the sky. In the early 2000s, it started finding quasars, not just distant ones, impossibly distant ones. Their light was stretched so far, the redshift so high, it placed them in an era the theorists had only sketched. And these weren't modest objects, they were blazing titans. The first one was a shock. Each subsequent record breaker over the next decade was a deeper shock. They pushed the epoch of formation earlier and earlier. The universe kept presenting monsters where the timeline said there should only be infants. That was the first major pivot. From theoretical prediction to confronting a stubborn, brilliant fact, for a while these quasars were the entire story, freaks of nature, luminous outliers. We could see them because they screamed so loudly, but they left a haunting question. Were they the whole population, or were they just the loudest members of a hidden crowd? That question defined the next phase. The arrival of the James Webb Space Telescope marks the transition. We're no longer just discovering the brightest beacons. We're beginning to take attendance. Webb's power lets us peer into smaller, fainter, more typical galaxies from that same ancient era. We're moving from the age of astonishing discovery to the age of statistical analysis. It's the difference between spotting a single, towering giant on a distant shore and finally mapping the entire coastline to see how many giants stand there. This historical arc is science in motion. A bold prediction meets an unexpected observation. That contradiction sparks a race of new ideas, direct collapse, primordial seeds, Super-Eddington feasts. And now the methodical work begins, gathering evidence not from one spectacular object, but from dozens, hundreds, to see which idea fits the pattern of the real, early universe. This is how understanding deepens, not in a single eureka moment, but in the patient accumulation of light from the deepest dark until a new picture slowly comes into focus. That early imbalance between a black hole and its young galaxy, it's not just a fact, it's a loaded gun. The consequences of that imbalance, they echo for billions of years. They shape the whole life story of a galaxy. The monster at the center isn't passive. It's an active participant, often a violent one. When it feeds, it doesn't just grow. It broadcasts, it sends out fierce winds of radiation, colossal jets of energy. That's the feedback we mentioned, but on a galactic scale, that energy floods out into the surrounding gas clouds, the raw material for new stars. The feedback heats that gas, it stirs it up, it can blow it clean out of the galaxy. And in doing that, it can shut down the production line, stop new stars from forming. A galaxy is born in a frenzy of star formation, glowing blue and white with young, hot suns. But if its central black hole activates too soon, too powerfully, that frenzy gets cut short. The galaxy ages prematurely. Its star-forming gas gets depleted or heated into uselessness. Over time, that blue-white glow fades. What's left is the cooler, redder light of aging stars. Astronomers call that a red and dead elliptical galaxy. It's a quiet, fossilized city. Its era of construction is over, so the implication is profound. If supermassive black holes became colossal in the first few 100 million years, they could have started this quenching process almost immediately. The destiny of a galaxy, whether it stays a star-forming spiral like the Milky Way for billions of years, or becomes a red and dead relic, that may have been decided in its explosive infancy by the monster it nurtured at its heart. The race to explain these infant giants is also a race to understand the primary architect of galactic fate. We're tracing a line from the first microsecond of quantum fluctuation to the formation of a gravitational seed, to the blazing quasar that heats its galactic nursery, to the silent, red giant elliptical galaxy we see today. The seeds of a galaxy's long, quiet decline may have been planted in the furious violence of its birth. It changes how we see the cosmos. It's not a collection of isolated objects. It's a web of intimate, violent relationships, where the birth of the largest darkness directly shapes the life and death of the largest lights. A galaxy's spin doesn't just go away. It's a kind of inertia. It resists collapse. You have this huge cloud of gas rotating slowly, drifting in the early universe. Gravity tries to pull it all inward to collapse it into something dense. But the spin pushes back. That angular momentum wants to keep things in wide orbits. It's a barrier. For a black hole to grow fast, it has to get past that. The gas has to lose its spin so it can move inward. and for a long time the models had trouble with this. The gas would just get stuck in orbit, like water circling a drain but never going down. It was a bottleneck. Then they added something to the simulations, something invisible, magnetic fields. In the early cosmos, those fields were probably everywhere, threaded through the gas like a tangled web, and they're not just there. A magnetic field exerts a force on charged particles. In that hot early gas, almost everything was charged. So these fields can act like a brake, a transport system. They can grab onto that stubborn spin, that angular momentum, and carry it away. Let the gas shed its orbital energy, slow down, and as it slows, it falls inward toward the gravity well. It's a subtle shift. The magnetic field becomes a facilitator. It doesn't make the food, it solves the delivery problem. More than that, these fields can channel the chaos. In a turbulent young galaxy, gas is flying everywhere. Magnetic fields can organize it. They can funnel diffuse clouds into focused streams, directing the flow straight to the galactic center, like guiding a river into a single aqueduct that feeds the heart of a city. It turns a disorganized drizzle into a targeted pipeline, a torrent aimed right at the black hole. The latest simulations show this. When they run models without magnetic fields, the gas often just swirls. It forms a stable, wide disk. The black hole starves. It grows slowly, but when they switch the magnetic physics on, the behavior changes. The disk becomes unstable. Fingers of magnetized gas reach inward. The accretion gets violent, efficient, a messy feast. So the invisible scaffold of magnetism might have been the secret ingredient, the unsung player. It could be the difference between a black hole that nibbles for eons and one that gorges itself into a supermassive giant almost overnight. The race to explain these early monsters isn't just about gravity and mass. It's also about understanding this silent, pervasive force that shaped the flow of everything, a force we can't see, but whose signature might be written in the very speed of their impossible growth. That magnetic field, it's this quiet background, and it leads to a deeper question, really a classic one in cosmology, the chicken or egg problem, which came first. The galaxy or the supermassive black hole at its center. Seeing these infant giants makes you ask, did a massive black hole seed form first, a kind of anchor in the early dark, pulling in the first gas to build a galaxy around it? Or did a galaxy start forming first, its shape made by dark matter's gravity, with a black hole only coming later in the dense center? This isn't just a riddle. It's about cause and effect in how the universe is built. The answer is probably a complex, back-and-forth relationship, a dance where each one influences the other from the start. But the timing, the trigger, that's everything. These early giants we see, billion solar mass black holes in galaxies that are barely there, they suggest the black hole's influence was there almost immediately. Its gravity, its feeding, started shaping its home while that home was still forming. So the hierarchy of how things are built might be upside down from the old story. Maybe the darkest objects aren't the final product of a galaxy's life. Maybe they're the foundational seeds for its birth. Solving this means unraveling the very first steps of a dance. A three-part dance between normal matter, dark matter, and the darkest objects. It asks which force led and which followed in building the structures we live in. The next generation of telescopes is coming. We're building new hunters. The whole effort to understand these ancient giants is moving into a more precise phase. Each mission is a specialist. Each one is meant to answer a specific question the current data leaves hanging. First, the Nancy Grace Roman Space Telescope. It's like a cosmic census taker. It has an incredibly wide lens. Webb looks deep at a tiny spot. Roman will take sweeping portraits. Its surveys will scan huge volumes of the early universe. Its main goal is to find more of those early quasars, the brilliant ones but also the fainter ones Webb could miss. It'll tell us statistically how common these objects were. Were they one in a million accidents, or were they a standard feature of the young cosmos? Roman will give us the numbers. Then there's LISA, the Laser Interferometer Space Antenna. This isn't a telescope for light. It's a microphone for space-time, 3 spacecraft forming a triangle millions of miles across, linked by lasers. It will listen. Its only job is to detect low-frequency gravitational waves, the deep, rumbling bass notes from mergers of supermassive black holes. When 2 of those billion solar mass giants spiral together, they shake the fabric of the universe. Ground-based detectors can't hear that. LISA will hear it. It'll give us a direct recording of those ancient collisions, a history book of mergers. It'll tell us how often these monsters combined in the cosmic dawn. It's the ultimate test for theories of growth through violent union. On the ground, another colossal project is rising, the Square-Kilometer Array, a forest of radio dishes across 2 continents. It will tune into the faintest radio whispers from the early universe, specifically the signal from neutral hydrogen gas, the raw material of everything. By mapping this primordial hydrogen, the SKA will paint a 3D picture of the cosmic web as it first formed. It'll show us the vast reservoirs of gas that fed the first galaxies. And crucially, it will show how the furious energy from an infant quasar, its jets and radiation heated and disrupted the gas around it. It will show us feedback in action back then. And for sheer detail, we look to the extremely large telescope, the ELT, a mirror 39 meters across on a mountaintop in Chile. Its power is resolution. It will take the faint, stretched light from an early quasar and split it into the most detailed spectrum we've ever seen. Every subtle line, every shift will be clearer. That allows for far more precise measurements. The black hole's mass, its spin, the composition of the gas falling in. It will turn a blurry fingerprint into a high-definition portrait. This whole arsenal is a coordinated strategy. Roman finds them, LISA hears their collisions, the SKA maps their food supply, the ILT scrutinizes their intimate details. Together, they promise a data revolution, a flood of evidence so comprehensive it will strain our theories to the breaking point. Comfortable ideas will be challenged. Radical ones will be tested, some will fall away. The coming decades won't bring a quiet end to this mystery. They'll amplify it, they'll refine it, they'll give us a sharper, stranger, and more beautiful picture of how our universe began. This epic quest is just leaving the starting line. The evidence keeps building up, but there's still this profound silence. We're listening with our best tools, and yet the earliest moments of the universe hold their secrets. Close in this race to explain these infant giants, we have to pause. We have to acknowledge a quiet truth, a humbling one. There are limits, hard limits to what we can know right now. We're detectives working with the faintest echoes, a photon that's traveled for over 13 billion years, stretched and weakened, a subtle tremor in a laser beam. These are whispers from an epoch of extreme physics filtered through incomprehensible time. Our models, these brilliant simulations running in supercomputers, they're masterpieces of simplification. They take the unfathomable complexity of a newborn cosmos, the seething quantum fields, the chaotic magnetohydrodynamics, feedback loops within feedback loops, and they reduce it to equations our computers can handle. It's a necessary approximation, but it is an approximation. The real early universe was undoubtedly messier, more violent, more inventive than any simulation can capture. There may be physical processes at play in those extreme densities and temperatures, processes our textbooks haven't described yet. A subtle interaction between dark matter and ordinary matter we haven't conceived. A property of spacetime itself under such strain that it alters how gravity works. On the largest scales, the true answer to how these black holes formed so quickly might not be a single, elegant theory. It might be a messy, combined recipe. A dash of direct collapse here, a period of Super-Eddington feasting there, all set to the background hum of primordial seeds, or it could be something we haven't even dared to imagine yet. A mechanism that resides in the gap between quantum gravity and cosmology. This admission isn't a surrender, it's the very engine of science. This humility in the face of the data is a profound strength. The enduring mystery of these early supermassive black holes is a gift. It's a powerful reminder that the universe is not obliged to conform to our intuition or to our current mathematics. It is stranger, more wonderful, more creative than we can possibly imagine, and that means the pursuit of understanding it isn't a path with a final destination. It's an endless, unfolding journey. Each answer reveals deeper questions. Each solved puzzle unveils a grander, more beautiful mystery. The infant giants aren't just objects in space. They are signposts pointing us toward the next frontier of human curiosity. Maybe the universe wasn't telling just one story. It might have written that first chapter in a few different ways. Those quasars we see from the very beginning, they might not all have the same start. With all the new data from telescopes like Webb, the job isn't just to have a good idea anymore. It's to fit those ideas together into one story that makes sense of everything, a single theory for how those first giants were born. It's like a detective finally hearing from enough witnesses to see the whole picture. For a long time, each witness, each model had its own story. The direct collapse story talked about a rare, quiet cloud collapsing on itself. The Super-Eddington story was about a frantic, chaotic feast. The Primordial story said the seed was there from the very start. Each one could explain a piece of what we see, but could any one of them explain all of it? The new data says probably not. The early universe was a diverse place. Some areas were calm, vast pools of pure gas, perfect for a direct collapse. Others were turbulent, where galaxies crashed together and funneled fuel in huge bursts, just right for Super-Eddington growth. And maybe mixed in with all that were those ancient knots, primordial black holes, already there as anchors, so the answer won't be picking one of these paths. It'll be a combination, a map showing where and when each path was the most likely way to build a monster. It has to account for the whole population. Not just the brightest quasars, but also the fainter black holes Webb is finding in smaller galaxies. It has to explain why some early black holes seem way too big for their galaxies, while others seem more balanced. It has to tell us how common they really were. This is where the real work is happening now. It's not a single eureka moment. It's more about patient pattern recognition. Astronomers are overlaying maps of early gas with maps of black hole locations. They're comparing the chemical makeup of host galaxies with the growth history of their black holes. They're running simulations that include multiple formation channels at once to see which mix matches the messy skyweb shows us. From all that careful work, a new standard model will come. One built not on elegant assumptions but on hard evidence. It'll describe the early universe not as a place with one rule, but as a grand experiment with many trials running at the same time. A lab where gravity tried every possible shortcut to making darkness. Our understanding of how structure forms is being rewritten slowly into something richer, more complex, a tapestry that finally matches the breathtaking, varied chaos of how it all began. The data and the models, they all have a human face behind them. Every quasar in a catalog, it means someone was looking at a screen, coffee gone cold. The whole mystery moves forward because of these small, human moments. A graduate student in Arizona working late sees something in a Webb spectrum, a faint line where there shouldn't be one. Their heart skips. It could be nothing. Just a glitch, or it could be cold gas around a black hole nobody's seen. That spark of curiosity, that private maybe, it's what fuels everything. A theorist in Tokyo, they're staring at a whiteboard covered in equations. Stuck for weeks on how the gas loses its spin. Then, on a walk in the park, a connection forms. The magnetic fields, they could act as a brake, not just a channel. It's a flash of insight, a quiet eureka, and they rush back to their laptop to change the simulation. That personal breakthrough from persistence, it might become a paragraph in the next paper. A paragraph that shifts the field. And then there are the veterans, scientists who have spent their whole careers on this. They remember the first high redshift quasar, a shocking point on a graph. They've seen theories come and go, refined or discarded by new evidence. Now, with Webb's data, they're seeing a transformation. Questions they asked decades ago, questions that seemed almost philosophical, are now questions you can answer with data. There's a deep satisfaction in that, and a humility seeing the universe stay several steps ahead. It's a global effort, collaborative, but it's also a gentle competition. Teams from different continents, they're looking at the same patch of sky, racing to publish first, to propose the most elegant model. But this competition, it exists inside a shared curiosity. They meet at conferences, on Zoom calls across time zones, debating passionately, but with a common goal: to understand. A postdoc in Chile shares a raw algorithm with someone in Germany because solving the puzzle matters more than the credit. Their stories are made of long nights and sudden breakthroughs, the frustration of a failed proposal, the joy of a paper accepted. This human tapestry of perseverance, collaboration, wonder, it's the real engine of the search. It reminds you the journey to understand the cosmos isn't a cold process. It's a human adventure. It connects our desire to know where we came from to this patient, collective work of turning starlight into understanding. The infant black holes are ancient, alien, but the quest to find them is vividly our own. The story of these infant giants is a mirror. It shows us our own understanding. And it reflects a cosmos that's far more inventive than we assumed, less predictable. We started with a simple fact, a shocking one: brilliant beacons where there should have been only darkness. That contradiction sparked a global race, a race that's taken us from the first impossible quasars in Sloan's data to the deep field images from the James Webb Space Telescope. We've explored theoretical landscapes, pristine clouds collapsing into massive seeds, quantum ripples from the Big Bang becoming gravitational anchors. Young black holes binging on chaos, breaking all the rules. This is more than an academic puzzle about distant objects. It's a re-examination of cosmic childhood. We're being forced to rewrite the biography of the universe from its very first pages. The answer will reshape our understanding of how structure emerges, how simplicity gives birth to staggering complexity. It challenges the narrative of gradual growth. It suggests the universe's largest darkness may have been its first architect. Its most influential one. This quest shows the best of the scientific endeavor. It's curiosity-driven, a mystery that pulled us in because it was there. It demands unprecedented collaboration. Experts in particle physics, cosmology, supercomputing, engineering. It fuels breathtaking technological innovation. Gold-plated mirrors in space, laser networks listening for spacetime's tremors, and it requires intellectual courage to question long-held, comfortable narratives. To look at the rulebook of cosmic evolution and admit a crucial chapter is missing. We stand on the brink of a new era. The Nancy Grace Roman Telescope will conduct its vast census. LISA will open its ears to the bass notes of ancient mergers. The extremely large telescope will bring those faint smudges into focus. Each new observation brings us closer to a coherent story. A story that can finally explain how our universe built its first monsters. The finish line in this race is not an end. It's a new beginning for cosmology. Solving this mystery won't close the book. It will open a new volume, one that connects the quantum birth of spacetime to the majestic architecture of galaxies. It will give us a deeper origin story, a richer one, a stranger one, so keep looking up. The next chapter is being written right now, in the silent fall of ancient light onto our mirrors and sensors. We are all witnesses to this unfolding, participants in a human story of wonder, from a coffee-stained notepad in a quiet lab all the way out to the blazing heart of a quasar. A quasar that has been waiting over 13 billion years to tell us how it all began.